Is it working, right? Cell needs to be
Sir,
changed.
no. The Google went with sir. We'll go into tips. Sir's laptop.
Right. So, so we are actually discussing about the supervised learning, right? So we started with the dimensionality reduction, right? Principal component analysis, linear discriminant analysis, and then KLDA, kernel linear discriminant analysis. Today, what we are going to discuss is about the regression model, right? Basically, all machine learning applications, right? So broadly comes under these two categories, right? Either classification or the regression. So today what we are going to discuss is about this regression. So what is that about? So in case of classification, what we do here is, right? So you would like to know this or this or this. We have only finite choices you will be given, and you need to identify that one among that, right? With what type of detection it is, for example, in telecommunication applications, right? So it is, that is a detection, but sometimes we may need to estimate the value itself. That comes under this regression problem, right? So you would like to estimate what could be the value of the channel coefficient, for example, right? Based on what you receive, based on, right, the pilot signal transmitted from the transmitter, based on what you receive in the receiver, you would like to know how to estimate the channel coefficient, right? In that case, it is not coming under what? The detection theory, right? We would like to know what could be the value of H, right? So it is more of continuous, right? We would like to know what is the value of that, right? So that is the regression problem, right? So mathematically, how we define this regression, how you model, right? So that's what we are going to discuss. This is the popular model. What we are going to discuss is what we call it as this linear regression. Doesn't mean that it is going to do fitting of what the linear, I mean, like a straight line, right? Not like that. Linear regression, here this linear indicate that this is a linear combinations of the weights with a basis function. The model is like this. This is the model. T equal to W transpose phi of x plus epsilon, right? So this is the model here. So let me tell you that this is the vector, right? You have this vector x. What is given here is the bold is a vector here, right? So let us say that you have the elements in these vectors, right? For instance, let me take it as x1 and x2, right? So two elements. This is the input, right? So which influences the observation? Which influences the observation? The observation is T here. T is the observation, which is basically the noisy observation, right? It is a noisy one. Okay. So you have this, say for example, this case, right? You are going to apply this phi, right? It is a basis function. You are going to have as many number of basis function as you like. I mean, we will come to that one, how to fix all those things. But so what is that it is going to do, right? So phi naught of x. Remember that the input to this basis function is a vector, and it is multiplied with a scalar w naught, right? Plus w1 phi 1 of x plus w2 phi 2 of x. Let us consider here only three coefficients here, W0, W1 and W2, but you normally have more, right? Hundreds of coefficients available, right? In general, and these are all what we call it as the basis function, and I will come to that also. I'll tell you what are all the basis functions available and how to choose, right? Depends upon the requirement, right? So now I hope this is clear to you, right? Up to this is clear, right? So you have what actually you are given is a data. What is a data? You will have a, now I am writing it as a vector. Don't get confused with this x1. This x1 is the first element of this vector x, okay? So now I am calling this x1 itself as a vector, right? So this is different. So it means it is the outcome of this one. That's what I'm talking about. This is a vector, right? Right. So this one is the input, and we have the corresponding observations like T1, right? So I hope this is clear, right? So what does it mean? For example, in a a simple circuit, right? You have that RLC, resistor, inductor, capacitors with so many components in it, and that is influencing maybe, for example, voltage at some point, right? So you can have this elements RLC, right? So these values are what I'm calling it as an input. You are controlling that. You are changing some R value, L value, C value, and you are finding out a particular voltage at particular node. That is going to be the observation. What you observe is going to be your noise, right? So what you observe is a noisy observation. It is not a, it is not the function of just RLC. It is going to have a noise component also available. That's what I mean. It's a noise observation. It's called as T1, right? So now you have for another combinations of RLC for this example, right? You are going to have the observation again. It is a noise observation T2, right? So it is going to have like this T3 and so on, and you are having n observations xn, and then the corresponding the target, right? So it is going to be the Tn here, right? So all these values, whatever you are having, they are all the scalars. And here, this is the input for this, right? I hope now it is very clear, right? And this T1 is a noisy one, right? So which we are going to model them as a, using that parameter what we are introducing. This is what we call as a parametric approach, right? So a parameter what we are introducing is these coefficients. W0, W1, W2. These are all the three coefficients. Here we have chosen only three, right? But in general, we can have more than that also, right? So T1 is modeled as, right? So W transpose phi of x1. This is there, right? As a main, right, relationship between this x and t. But very important is the second term, which is the epsilon. Epsilon is a random variable. Epsilon is the random variable that follows this Gaussian distributed with mean 0. Variance, let us consider that as 1 by beta, right? So that makes this observation T1 going to be the noisy. So for the same set of RLC, when I measure that voltage again, it is not going to be the same value, right? First time you will get 2.3, second time you will get 2.34, right? You have some fluctuations in that because of this noise added to it, right? So that is actually contributed by this epsilon. Whatever we observe, all are going to be that noisy observation. So here it is going to be W transpose phi of x2 plus epsilon, right? So it goes like that. And finally here it is W transpose phi of xn plus epsilon, right? Right? So now what is our goal? Our goal is for the new set of values, right? So for a new set of value given RLC, I would like to know what is the voltage, right? In fact, what really it means is W transpose phi of x test. If I am giving the test vector, right, x test, I would like to know what is that corresponding value of the voltage, right? I mean, in this case, I am taking that as a example, right? So this is what I want. W transpose phi of x test is what actually V naught. So if I expand this, it is nothing but W naught phi naught of what? X test, right? Plus W1 phi 1 of x test, and then W2 phi 2 of x test. Regression over. That's all. But what is left out, right? We are interested in knowing about these W's, right? Once we fix these W's, your regression problem gets over, right? So how to find out these W's? right? So there are many methods to do it. That's what we are going to discuss in detail, right? So the most important technique is, we call it a proper statistical method for this estimating this W vector, right? So which comes as the estimation problem, right? So whenever you want to estimate the outcome of some variable, I will give some small intro about that, then I will come back to this exact problem, right? For example, let us say that X is the random variable, right, which influence the random variable Y in some way. We have an inherent function in it, right? You got the point, right? So now, based on the observation of the outcome of the random variable X, say X1, you would like to know what could be the outcome of the random variable Y, which is basically this Y1, right? So that is what really we are doing. You are actually looking for the observation of one random variable, right? So X, here I'm taking it as a random variable only, not a vector for understanding, right? So we are observing the outcome of the random variable X. Based on that observation, you wanted to know what could be the outcome of the random variable Y, which there are having some inherent relationship between this Y and X. That's what the thing, right? So to do this, to handle this problem, as I define this X and Y, they are all the random variables, right? We have to go for what we call it as a density functions, right? So whenever we have such problems, we have to look for 3 density function, right, based on what random variable you want to estimate, right? So outcome of the random variable, what you wanted to estimate. Here, this random variable, what you wanted to estimate is Y, right? So with reference to that, we have something what is called, Fy of Y, which we call it as this prior density function. So this is the prior, right? And you have this, right, for a given value, right? X equal to X, right? So this is going to be what? The posterior. This is the posterior density function, right? And you have the other way around, right? So fx given y equal to y of x, which we call it as a likelihood function. These 3 density functions are important for this estimation, to know about what could be the value of y based on that observation of x, right? So what is that? What actually we are doing? I'll give you the intuitive idea again. I start with this intuitive idea, right? So what actually you are going to do here is, say for example, the outcome of the random variable x, right? So I'm having that outcome like this: 1.1, 1.2, 1.4, right? Then say 0.9, then 0.8, right? One more time I will put 1.8, then 1.2, then 1, 1.4, 1.4, 1.4, 1.4, right? The data are like this. These are all the outcome of the random variable x. Everything, all these things, right, is ending up with the same value for the random variable y. Say for example, or for all the cases, these are all the values of x, okay? For all these values, right, it is ending up with the same value of y. Say that value is, say for example, 3, right? You got this point what I'm doing? See, here I am having a different values of x, which is actually ending up with what? The identical value of what? Y, right? You got the point, right? So now you put it the other way around now. So let me put, this is one thing, right? So you can even have the other combinations, right? So here you are going to have this x value same. Say for example, I'm having x value same, right? 1, 1, 1, 1. Everything is 1. This is the x here. But it is ending up with different values of y. Let us say 3.1, 3.2, again 3.1, and then 3.0, then 2.9, right? Then 3.0, then 3.0, it goes like that, right? So this is x and this is y. Remember that for the same values of x, you are fixing x, that's the meaning of it. What you observe that random variable y, you are having at different values, but remember that there are some repetitions, right? I'm getting 3 twice, right? 3.1 twice, sometimes thrice and all, right? All these things are actually what? The probability of occurrence of various values of y, right? If it is a continuous case, we are talking about this continuous case, this is actually described by what is called the density function. It is an arbitrary density function, not like a Gaussian or any shape. It is some arbitrary density function you are having, right? So what is this density function really gives you? This is y here. This is the density function of y only. But here what I am giving, very important, by fixing that x value as 1. I am fixing x equal to 1, but I am getting a different values of y. I am looking for how that y is distributed. The density function I am looking for, right? As such, the density functional value will not gives you what? The probability, you know that if I have a small interval over this y, right? So which we call that as a delta y, then this area will end up with what? The probability. I hope these things and all you know, right? Because density function as such will not give you the probability, right? But if you take this small delta y, then that will give you the probability, right? So now it is a very common sense now, right? Now the common sense is for x equal to 1, what could be your choice for y? I have x given as an input, right? 1, right? So what could be the choice for y? Very simple. Immediately what do you say? Huh? What do you say from this figure? What is the choice? Huh? Yes, that is one choice, right? This is one of the choice, right? So what I can have, right? This is the one choice, because what is the meaning of that? Same values of x ending up with this particular y, this particular y many times. That is a peak. Though we get all other y's, but it is better, safe, and it is good that if I declare that y value is what? Y cap. You got this point? Not getting? Right? So what I'm saying here is, you are fixing this x. You are fixing x, same x. I'm getting all many values for y. If it is 1 to 1, no problem, but that is the issue, right? We are not getting that single value, right? You are, because it's a noisy observation. I already told the observations are noisy, right? Every time you are getting different values. I'm getting 3.1 sometime, 2.9 sometime, and 3.6 sometime, like that. It is having all possible values, because Gaussian noise all the way it goes up to what? Infinity. This side is also, it goes to minus infinity, right? It can have any value, right? So x is fine, but what you observe y, right? So it can take any value. So what could be the better choice for selecting that y for a given x? The choice is one of the choice I'm telling. This is nothing but your peak value, right? So this is what we call it as the map estimate. Basically what we are doing here is the map estimate, maximum a posteriori probability density function, right? So the posteriori density function where you are getting this maximum, right? So that is what you are going to declare that as a estimate. Okay, fine. What are the other choice? Of course, right? So when we talk about this is nothing but a mode, right? This is nothing but a conditional mode. You are giving that condition for x, and then you are actually finding out the mode value, right? The peak value, right? This is what we call as a conditional mode. Obviously in statistic, what are the other two things we are having, right? One is the conditional mean. The another one is the conditional median. Yes, that is what the solution is. There are three solutions actually for this regression problem, right? So one is MMSC, and we have this MMAE, and then we have map. Map I already told, right? So this is the conditional mode, right? And this is the conditional mean, right? And this is the conditional median, right? So what does it mean? See, conditional mean, if I want to know what is that actually it is going to do, it is going to find out the expectation of y given the value of x is what? 1. So this is what we say that it is a conditional mean, right? So I mean, if I want to expand it in a mathematical way, what actually we are doing here is we are actually finding out the density function, right? Fy given x equal to 1 of y, right? So how to find out the mean, right? Y into Fy given x equal to 1 of y dy, right? So this is basically the expectation. Got it? I mean, expectation of y into the density function, right? So that is what gives you the expectation, right? This is one of the choice. This is one of the choice for this y. What is the next choice? I mean, third choice. I mean, we call it as a conditional median. In case of conditional median, what we do here is we look for a point. I mean, the same density function I will take here. The same density function I will take. So maybe nearby I will take here this point, right? So this is going to be already mapped. This is the map estimate, right? This is the map estimate. So I'm just selecting this point nearby, right? So the area all the way from minus infinity to this, right? So it goes like that, right? So all the way from minus infinity to this point, right? And if I take the area in the right hand side, right? So it is the area from that point to infinity, right? You got this, right? So these two are going to be that equal, right? So it means that minus infinity to, you are going to have this y cap, we called it as a MMAE, right? And then you have the density function Fy given x equal to 1 of y dy, that is equal to what? Y cap MMAE to what? Infinity Fy given x equal to 1 of y dy. I am taking these two area to be the same, and this value is the good estimate. This is going to be the regression estimate, right, for the given value of x. For a given value of x equal to 1, the estimate of that y is like this, right? So you have all the three combinations. These three are there, right? Right? But in this case, what actually we are interested is this, the posterior density function, right? So the posterior density function is needed to do what? MMSC, MMAE as well as this map, right? But unfortunately, that is not available in the model what we normally do. Even in case of this regression problem for estimating this W, right? It is hardly, right, difficult to get this posterior density function, right? So what we do here is we use this Bayes relationship relating this posterior density function and the likelihood function. They are interrelated, right? So we use this relationship, right? And then we apply this map, right? So how they are related? First of all, Fy given x equal to x of y. This is something like, if I want to have a comparison with the probability, which is nothing but probability of AB given what? Probability of B, and then this is probability of B given A into probability of A given, divided by probability of B, right? So the similar fashion we can actually write in the density function form here, right? So this is going to be our fx given y equal to y of x, right? So into what? Into fy of y, right? Whole divided by fx of x, right? So the similar setup what we are having for the continuous case in relating this density function, right? So what we are interested is y. You have to clear in that what our requirement is to find out y that maximizes this, right? So you would like to know what is the maximum value of this density function. I'm talking about this map. In case of map, we are interested in finding out this maximum value of this, right? Which is exactly equivalent to what? Maximizing this in the right hand side. I would like to find out the value of y that maximizes what is there in the right hand side. What is there in the denominator, right? This fx of x is nowhere related with y, so that is not going to play the role in maximizing whatever is there in the right hand side. And of course, numerator plays the role, but this is the biggest assumption what I'm going to tell now, right? This fy of y, because we don't know, that's the problem, right? If I know fy of y, obviously I can get my posterior density function, then I can go for MMSE, MMAE map. Remember that MMSE, MMAE map, they are all the best solution, right? That you have to keep in mind. But unfortunately, that those things we are not able to get in practice, right? So what normally we do here is fy of y, we treat them as a constant, treating it as a uniform distributed. It is just simply constant. So here what we do here is this one, right? Fx given y equal to y of x, right? This is nothing but a likelihood function. Instead of maximizing this posterior density function, we maximize what is called the likelihood function, keeping that Fy of y as constant. This estimate is what we call it as the maximum likelihood estimate. If you see the paper, research papers, many techniques, right? So they actually use this maximum likelihood estimation for the simplicity, right? Because we don't have a model for the posterior density function. If you have it, it is fine, but if not, then we have to go for what is called this maximum likelihood estimation, right? Here in this case also, we are actually going for the maximum likelihood estimate, right? So this is what I told, right? So these things already told. Let me finish and then I'll give the chance for you to ask the questions. I guess you will get it if I give the details, right? So I don't want to have a interrupt in the middle, right? So that you will get it anyhow, right? So what I want to concentrate more on how to estimate W, that is what is needed. So I'll simply summarize here what we discussed so far, then I hope you will get it, right? So we got a model, right? So what is the model? Y of x is what? W transpose phi of x, right? No, this is the model. Y of x is W transpose phi of x is the model. But T is the observation, which is the noise, which is basically this Y of x plus epsilon. That is the model. Okay. So what we observe is T only, but what I need is this Y of x. This Y of x is related with what? This x using this W transpose phi of x, right? This basis function phi of x, we are going to fix it. Phi naught of x, phi 1 of x depends upon the basis function. That will be the known value. We know the value because I can substitute that value in that function. I get a value out of it. What is not known is actually this W, right? So with reference to this W, right? So W means it is a vector actually in this case, right? So you have, for example, W0, W1 and so on up to this Wm minus 1, right? So in general, M minus 1, M elements are there in the W vector, right? In the previous slide, I showed only 3 elements. Here, more generally, it is about M elements we are having for this W vector. I hope this is clear to you, right? So we need to estimate W. So once you want to estimate W, right, I already told. So what I told is only the technique, right, how to attack this problem. We are going for this estimate of W. So for that, what are the density functions you need? You need, because we are interested in estimating W, right? So what are the density functions you need? You need this prior density function. You need the posterior density function, f of W given the observation. What is the observation you are having? The observations are T1, T2 and so on up to this Tn, because that is the data given to you, right? And then corresponding values of x1, x2 and so on up to this xn. You got the point, because that is all the data is given. Condition on x1, x2, x3 and so on up to this xn and the corresponding observations, right? T1, T2, T3 and so on, right? Given that condition, you need this density functional value, right? F of W, right? So, and the third one, what is that? Third one is the likelihood function, right? So, in this case, this likelihood function is what? T1, T2 and so on up to this Tn, right? Given W. And I am not bringing this x here because x is the input. T is actually the observation. X is the input, which is the fixed value. T is observation, which comes under the random variable, right? So x, in fact, here itself is not really needed, but for the completion, right, I am giving that. But likelihood function is this. You got it, right? F of T1, T2, T3, and so on up to this Tn given W, right? So this is going to be your likelihood function. You got this point, right? So now what we are going to do here is we are going to maximize this likelihood function, right? So in fact, I told there are 3 solutions. For all the 3 solutions, what really we need is this density function. This is the posterior density function. We need that. Once this density function is known, then I can go for 3 choice, right? One is what? Conditional mean, conditional median, conditional mode. Fine, that is the best. But we are not going to do now, right? So we are going to use this ML, maximum likelihood estimation, right? So for that, we are going to maximize this. So why I'm telling this is easy? Because this model is simple. Why? Because we have t equal to what? Y of x plus epsilon, right? So let me put it as like t1 equal to what? Y of x1 plus epsilon. Now can you tell me what is the density function t1? Epsilon, you know that it is Gaussian with mean 0 and variance as what? 1 by beta. And x1 is the specific input, right? So y of x1 is some functional value, right? That's what we are interested, right? But as far as this expression is considered, y of x1 is nothing but a constant, right? Epsilon is the random variable, right? It's because it is going to have a different values in it. It's a noise, right? Y of x1 is the constants. So now tell me how this t1 is distributed. Excellent, excellent, excellent. Very good, very good. So mean alone is going to get shifted, right? Y of x1 and the variance remains the same. That's what I said. It is easy now to model the likelihood function rather than the posterior density function, right? So T1 is modeled as simple Gaussian, right? So you know the expression, right? 1 by root of 2 pi sigma square. Sigma square is 1 by beta. So we can put it like this, right? And then e power minus, what is that? T1 minus mean is what? Mean is what? Y of x1. Y of x1 is nothing but W transpose phi of x1 the whole square by 2 sigma square, which is nothing but 2 by beta. So simple. This is the density function for what? T1. Same thing for T2. Only thing is what is going to change here, right? So this will change to what? T2 and 2 here, right? Isn't it? So in more general, I can put it as K here, right? For the kth T value, right? So observation, right? Sorry. So you are going to have for general case, it is K here, and here also it is going to be that K here, right? All these T's, T1, T2, T3, and so on up to this Tn, they are independent. They are observed as what? They independent. They are totally independent to each other, right? So if I want to know about the density function of T1, T2, and so on up to this Tn, it is simply the product, right? The product of K, I mean, over the K ranging from 1 to n, all the observations here you are having. So I already told that you wanted to maximize this. I want to find out W that maximizes this, right? So to do that, of course, logarithmic function is the increasing function. So maximizing this is same as that of maximizing the logarithm of this function. When I take this logarithm with the base e, this constant is not going to play the role in getting it maximized. Only this is playing the role, right? So when I take this ln for it, what is that you get? You get minus what? I mean, this product will become what? Product will become, anybody? Excellent. K equal to 1 to n, and then what will happen? Tk minus W transpose phi of xk the whole square. Of course, we have some constant in it. That is also not really needed, right? You got it? This is what actually you wanted to maximize. But remember that there is a negative sign here. If I remove that negative sign, the problem will become what? Minimize, right? So that's the thing, right? So you wanted to minimize this problem. I mean, minimize this function, right? So this is the classical dash. What is that? What is this problem called? Least square. Excellent. Very good. This is nothing but a least square problem, right? So max least square problem, right? So we are going for this least square solution, right? So maximum likelihood estimation boils down to what? The least square solution. When dash, what is that? When under what condition it is actually becoming the least square? One important condition we used, what is that? Only because of that it is actually become the least square, otherwise it will not. Huh? No. Not that point I am asking. Huh? No, that's okay. That's a likelihood function, right? I mean, one important property we assumed. What is it? Huh? That's all okay. Yeah, that is okay. That is okay. IID, we are taking independent density. That's all important, very important. I mean, these are all important only. Still one very important. Let me put like this, right? So that alone is actually making this problem as the least square. What is that assumption we made? Huh? No, that's okay. That's the point. We assumed the noise is Gaussian. That is a major, see, don't take granted that noise means Gaussian, right? We cannot always say that it is going to be that Gaussian. It could be something else also, right? We assumed the noise is Gaussian. Gaussian only makes the whole structure like this, I mean, whole square, all those things, right? If I have a different epsilon here, if I have a different model for this epsilon, you will get a different actually that expression, right? So that you got this point, right? So the maximum likelihood estimation ends up with what? The least square problem when the noise, I mean that additive noise is modeled as what? Gaussian, right? So now, so that's the thing, right? So we wanted to minimize this. That's it, right? Sigma k equal to 1 to n tk minus what? W transpose phi of xk the whole square, right? So we have some observations, right? So you are given a data and you wanted to minimize this, right? So using this least square technique, right? So you have like x1 and then we have this corresponding t1 and then you have x2 and then corresponding t2 and it goes like that. You are given this xn and then you have that corresponding tn. These are all the data given to you, right? So how to, right, find out this w that minimizes this least square, right? So this is, yeah, this is what I was telling. Yes, right, right, yeah, right. This is maximum likelihood estimation and this is the density function, right, taking logarithm, right, and you wanted to what, maximize this, right, and removing that negative part, it becomes a minimization problem, becomes a least square solution, right? So now what is the solution? The solution, what you are going to do here is, we are going to write like AX, right? Because we have the observation for what? X1, X2, up to this Xn, all are what? The inputs, right? And you have the observation which is basically the noisy observation. In fact, what is this? This T1, T2, T3, they are the noisy observation. In fact, what I'm telling here is this needs to be added with what? The noise component in it, right? This, yeah, epsilon, right? So it is basically for every row, right? This row multiplied with this column will get a single element scalar and that is added with some outcome of the epsilon. The outcome of epsilon, let me write it like something like epsilon 1, epsilon 2 and so on, right? So there are the outcomes of the random variable epsilon which is actually contributing the noise, right? This is actually the expression, but what we do here is we construct the problem like a simple ax equal to b problem, right? So removing this this noise part, right? This is matrix A and this is x and this is b here. Whatever you observe, this is the observation here, and this matrix A is constructed using what? The basis function, right? So it is simply what? Phi naught of x1 plus phi 1 of x1 into up to what? Phi m minus 1 of x1 is correspondingly we have to multiply with what? The w's, the first model, right? Which is basically that y of what? X1, right? So which is nothing but what? W naught phi naught of x1, the w1 phi 1 of x1, it goes all the way up to what? W m minus 1 of phi m minus 1 of x1, right? So this is what is y of x1 and this is this one first second row, that this column it will end up with what? Y of x2 and so on. You got this point, right? So now this is of the form ax equal to b. We need to solve this, right? First of all, this matrix A is not a square matrix, right? So you can have as many observations right? N and this M will be a different. It is basically a rectangular, depends upon the value of N and M, right? It could be the tall or, right? So this way or this way, right? So it can be in a fat type of thing, right? But we would like to know about this W. That is the problem, right? So we would like to know about this W and B, this vector B, whatever you observed, need not be in the column space of the matrix A, right? So we need a solution for X. Anybody? What is the solution for this? I mean, best estimate of X when B is not in the column space of A. So you know what I'm talking, right? I mean, we need a solution for X, right? So it looks like a very simple linear algebra, right? Ax equal to B. We need to know about the value of X, right? But B, right, needs to be in the column space of A, then only that X exists, solution exists, right? Is it not? Right? So what I'm trying to say here is the matrix A, right? You are going to have some column vectors like this, right? Say for example, in this case, it is going to be M column vectors available, and your unknown variables are W's, right? It goes like this, Wm minus 1, and the output is going to be what? T1, T2, and so on up to this Tn. Right? Each column is of size n cross 1. This matrix is of size n cross m here, and this is going to be your what? M cross 1, and this is going to be your n cross 1, right? See, what I'm trying to say here is these vectors, these column vectors, right? So these are all the column vectors. I am having a pictorial representation of these column vectors, A1, A2, and so on. This is going to be your AM, right? These are all the column vectors. I'm just taking the columns of the matrix A, right? And I am putting it as a vector, right? The linear combination of those vectors forms a space. So this is a vector space, right? So if this T, this is a vector T, this is a vector T, right? If this T lies in this here, you get a solution. I mean, just satisfying what? Ax equal to B. Exactly, right? So you can, but in practice, definitely it is not going to be there in the column space of right A. So your T is going to be somewhere here outside this space, right? Right? So what we do here is we project this vector to the column space of A, right? We project, and that project is what we call it as T cap, and we formulate the problem, right, like this, right? I mean, let me put it as the exact problem itself. The problem is phi W equal to T, right? This is the problem similar to this, right? So you want to find the solution for W. As I told you that the T is not going to be there in the what? The column space of this matrix phi. This is the matrix phi, right? So it is not going to be there, right? So what I'm going to do here is I'm going to reformulate like this, isn't it? Right? So you project the vector T to the column space of A, so that solution exists and I can get my W cap. And this projection, what you are going to do is the perpendicular projection, because I want that error, this T minus T cap to be, this is the error vector, right? I want this error vector to be as small as possible. So I need to do this perpendicular projections. I'm not going to do the proof and all, right? So the solution happens to be, right? It's a very simple proof, but I'm not going to do that, right? So the solution happens to be what? Phi transpose phi whole inverse phi transpose what? T. This is the solution. Regression, one of the solution we got it. This is what the regression model is, right? So y of x, what is y of x? Y of x is what? W transpose phi of x. We are interested in getting W. W is constructed using this matrix expression using the data collected, right? X1, X2, X3, and so on up to this Xn, right? You got the point, right? So given data, two steps only, right? Given data, construct this matrix and compute this W. That's all, right? So this is one solution I'm telling. One of the method to get the regression, right, model, right? So what is that you are getting? This is going to be your parametric approach, right? Right? Yes. Oh, okay. So, yeah, how to choose first of all M and what functions to be chosen. Everything needs to be discussed. Of course, I just show one figure alone, just because you raised, right? So you may have in your mind what type of how the basis function looks like. I don't know whether I kept it or not. I guess it is not there. See, the basis functions you have the choice like polynomial basis function, like phi naught of x always chosen as 1, phi 1 of x, phi 2 of x, in case of polynomial it is like x square, x cube, like that. In case of we can have a Gaussian basis that is more popular, and then we have what is called sigmoidal basis function. You can have many choice for it, right? So depends upon the requirement, right? So actually if we have some localization in your problem fitting, right? So if it is throughout the range, if it is having some proper variations linearly, non-linear, of course, it's gradually increasing or decreasing type of thing, it is okay. But if we have humps, right, ups and downs are there in the relationship, you have that relationship between what is the input and then output observations. If we have more number of peaks, then Gaussian basis is the best choice, right? If I have a curve like something goes on increasing or decreasing type of thing, but a different degree, then we can go for the polynomial, right? It's all depends upon trigonometry also we can use for if I have more oscillation type of relationship, then we can go for the trigonometry basis function, right? The basis function is actually the choice what you have to fix based on the visualization. Again, that is a problem for 1D and all we can see, but still, right, depends upon the nature of the relationship, we have to fix the basis function, right? So basis function is freezed. Once this basis function is freezed, we need to estimate W. That's all, only 2 steps. So what we have discussed is only maximum likelihood estimation that happens to be the least square solution when the noise is Gaussian, and the solution happens to be very simple, phi transpose phi whole inverse phi transpose t, right? With this, let me stop here and we will continue the other regression model and other techniques in the after. Yeah, now you can ask. Yeah. So you are summarizing again. No, I'm just asking what is the question I'm not getting. It's already there. Don't worry. Everything is there. See, what I'm telling here is now I told maximum likely, right? We are going to discuss about the posterior density also. What is not available in posterior density? Map is okay, fine. For your information, for the Gaussian case, map, MMSC, MMAE, all are going to be the same for Gaussian, right? ML, ML, we have to see what function is. In this case, it is also Gaussian, right? Okay. Yeah. See, for performing MMSC, MMAE map, what is really needed is the posterior density function. If you are able to model the posterior density function, you can go for map, you can go for MMSC, you can go for MMAE. It is possible. But the posterior density function, right? Yes, 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 absolutely. Yes. If you are able to get it in some form, right? For getting that, you have to assume f of w, for example, prior density function, because they are related, right? Yeah, exactly, exactly what you are saying. But we don't know, right? We can assume. That's what we are going to do that in the afternoon. We are not assuming anything as of now for the W, right? We are going to assume W also follows Gaussian, and then we are going to solve. That is what we are going to discuss in the afternoon. You are right. What you are saying is right. Yeah. Oh, okay. Sir, no, sir.
सर ये कहाँ पर इसका है स्टॉप रिकॉर्ड? हेलो, रिकॉर्डिंग टाइम करके लिख के आया। स्टॉप रिकॉर्डिंग कर दूं?
फिर से स्टार्ट कर दिया।
हाँ, उसके बाद यहाँ का स्टॉप। गाड़ी निकाल, गाड़ी निकालो। पीछे बैठो, पंचर गाड़ी में।